As you may recall from your statistics class, that we are to calculate the confidence interval, you need to know what is the number of observations you've been working with, and you need to specify the limits of the probabilities that you want to incorporate inside your confidence interval. You might have also remembered that for small observation data sets, we usually calculate the confidence interval using the t-statistic or the t-distribution. And for large data sets, we use the z-statistic. Therefore, when we go to calculate the upper limit, that is calculated as the mean plus z times the standard deviation of the sample divided by the square root of n, the number of samples. And the lower limit is the same calculation, except it's just mean minus that quantity there. And the z is what we get from the normal distribution. So if we go to draw a quick sketch of the normal distribution, our z values that we're trying to encapsulate, to sort of define the limits of what are all the uncertainty in our data, are what we want to find. And so the areas outside the z's, as you see there highlighted in yellow, is what we call our alpha value. In other words, the summation of the area under the curve from negative infinity to negative z plus the area under the curve from z to positive infinity. So that's the summation of those two areas is our alpha, and that alpha represents how much uncertainty we're willing to ignore, that we're comfortable ignoring when we report this value. To find out where that z value is along the probability distribution function, we do this little calculation, 1 minus alpha over 2, and that's going to give us the value of the probability from negative infinity up to positive z. Typically, we will use an alpha of 0.05. That's it's totally arbitrary. Somebody back in the day said, you know what, we like to consider 95% of all of the uncertainty, and that just kind of stuck. So we ended up using alpha of 0.05 all the time. That corresponds to a probability of 0.975. I know this may sound kind of confusing because we said, didn't we just say the alpha is 0.05, so wouldn't it be 0.95? But as you can see there, if in the probability table, in the probability distribution table that you have already, the integral goes from negative infinity to z, and because the confidence interval chops off the upper and lower tails, and the summation of the upper and lower tails is 5%, then that means each of the tails is only 2.5%, so it's actually 1 minus 2.5%. So that gets us 0.975. So the way Bulletin 17b talks about this, now remember we're talking about the log Pearson type 3 distribution. They have similar ways. So there's an upper limit that has a function that is this calculation, where the mean of the logs plus the k-statistic, the upward limit k-statistics times the standard deviation, that'll get you the upper limit of the projection of the 100-year flood or whatever it is you're trying to deal with. And then you still have to remember to calculate x up. All right. And then the lower limit is the same thing, but you have to change the k-statistic value. So there's a k up and a k lower, and that's the k-statistic is the statistic that corresponds to the log Pearson type 3 distribution. So k up is calculated using this formula. Notice the plus sign, and the k low is calculated the same formula but with a negative sign there. So what we don't know here is these a's and b's, as are kind of unfamiliar to you all. The case of t is, in this equation, it corresponds to the k value of a return period t. So the k statistic for a return period of t. So if it's a 100-year storm, it's the k statistic for the 100-year storm. So in this case, A is just this quantity, 1 minus z squared over 2 times the quantity n minus 1. And B is the k statistic squared minus the z statistic squared over n. So both, as you can see there, this confidence interval in its basic form is essentially a function of the number of observations and the probability that we're dealing with, or the z statistic, just like the other one, but we're kind of looking at it a little bit differently because we've got a different probability distribution we're working with here. So that z value, like I said, is the z statistic that we're working with. So let's do a quick example to sort of illustrate how this works. So let's say we've calculated that the 100-year flood for a given river is 3,808 CFS, so 3,808 CFS. And that the mean of the log stream flows is 3.1. The standard deviation of the log of the stream flows, standard deviation of the log of the stream flows, well, it's getting kind of a mouthful, is 0.289, and the skew is negative 0.7. And of course, the number of observations is 41 years. So what we want to do is find the 95% confidence limits. That means our alpha is 0.05. So we're going to take the typical road, the typical path here in this. So that means we need to find what is the z value at the probability equal to 0.9750. So before I tell you that answer, why don't you get out your probability distribution table and pause the video and go look that up right now. Tell me what is the z value. Get that ready to go. Alright, did you happen to get 1.96? Hope so, because that's the right one. So the z value, when we're out at 1.96, then there's only 2.5% remaining to the right tail. And then when we're at negative 1.96, there's 2.5% lower than that value. So what we're trying to find here is the k statistic corresponding to the 100-year event. So we go back to the log Pearson 3 table, we look up the skew as at negative 0.7, and we try to find where the probability is 0.01. So we find the k statistic that corresponds to a skew of negative 0.7 and a probability of 0.01. That would give us the 100-year k statistic. So why don't you go do that, go to the table that's also part of one of your handouts, and look up that value. Alright, so did you find this value, 1.80621? Hope so. Hopefully I found the right one. Hopefully you found the same one, and you're not cursing my name right now. So let's go ahead and calculate A and B. A is, pause the video and you do it yourself first, 0.952, that's what I got. So B is equal to, plug in all the numbers, and we have a place where you can pause the video and calculate the number yourself. 3.169, that's what I got. So just to save time calculating, I'm going to start by calculating the k statistic squared minus AB to the 1/2 there. And I get a value of 0.4955. Alright, so now we know we can substitute that into the k up and k low calculation. So let's do that now. K up equal to the k statistic at the 100-year mark plus that quantity we just calculated divided by A, and I do the same thing for k low, except for we're going to do the k statistic minus that quantity above there. And so these are the answers that I get here, 2.418 and 1.377. So go ahead and move over to the left a little bit. Didn't save enough room at the bottom there, but so go over to the left and calculate the y up and the y low. So I go back to the beginning. My y bar is 3.1, my k up is 2.418, and my standard deviation is 0.289. And the equation down below is the same thing there, except the k statistic is changed for the lower bound. And that gives me 3.8 for the upper Y up, and for the Y low is 3.5. But we're not done here because they're talking about these are in log units. So we need to take the anti-log of those values and get the X up is 6,310, and the X low is, let you do this one on your own. What do you think? Last number. Go ahead, press the buttons. Do it yourself. Alright. X low is 3,162 CFS. So that's the spread on the data. So what we're saying here, what this result tells us is that we project that but we estimate that the 100-year flood is 3,800 CFS. We, excuse me, if this calculation were run an infinite number of times, let's say a lot of times, we expect that 95% of these calculations would give us a value between 6,310 and 3,162. So that's what this really tells us, is that if we were to repeat this scenario, this calculation over and over again using different observed data, but along that same river, different observed data along that same river, maybe different intervals along the same place, if we did that over and over and over and over and over again, we would expect that 95% of the time we would be between 6,310 on the top and 3,162 on the bottom. So hopefully that helps. It's a fairly easy thing to do when you project your 100-year stream flow, to just plug these numbers in, especially if you take the time to get them ready and put them into Excel. So hopefully that helps you sort out how to do confidence intervals.